Hi everyone, this is my Physics 2211 Lab 5 report video. Here is a brief overview of what I'll be covering in this video. I'll start off with the introduction, then the fundamental principles, along with the procedures and experiment and analysis from Tracker. I will conclude with the sources of error and the discussion questions. Moving on to the introduction, the purpose of this lab was to examine and analyze the motion of a falling slinky and create a computational model based on the momentum principle. Some fundamental principles include gravity, tension, and drag. Tracker was used to analyze the video, and GlowScript was used to construct the computational model. A brief preview of my results is that there were some deviations in the final graph between the observed and predicted model. We used a computational model based on the momentum principle because it states that the net external force acting on a system causes a change in its momentum over time such that the net force is equal to delta P over delta T. Here we have the velocity update and position update formulas. The reasoning for using this principle is to allow us to calculate the velocity and position of the falling slinky. These formulas were derived from Newton's second law. Next, we have gravitational force and drag force. Gravitational force is given by 0, negative mg, 0, but in this case, it would be negative mg j hat, where j hat is 0, 1, 0. Drag force acts opposite to the object's motion and is given by F drag is equal to negative b v squared times v hat. The reasoning for using these fundamental principles is to predict how the slinky moves and how it accelerates, stretches, and slows as it falls. Now moving on to procedures and experiment, I screen recorded the falling slinky video from YouTube. I uploaded the video to Tracker to track the motion of the falling slinky in each frame. I then created a computational model using GlowScript to get the predicted trajectory of the slinky. I collected data from both Tracker and GlowScript to create spreadsheets, and lastly, I compared and contrasted the observed and predicted data points using Excel. In the falling slinky video, the system is the slinky and the surroundings include the earth, the air, and everything else. The mass of the slinky is around 0.25 kilograms, and the height of the person is 1.75 meters. The initial position of the slinky is 0.0368, negative 1.160 meters. And finally, the initial velocity of the slinky is 0. The initial conditions are highlighted in orange. Ball.m is equal to 0.25, which is from the previous slide, and again, the initial condition were set from Tracker data points. Ball.position is equal to 0.0368, negative 1.160, and the velocity is 0. B equals 30 was calculated through trial and error. In our first while loop, we have W is equal to negative ball.m times G times J hat. F of t is the tension force, and ball.velocity and ball.position are calculated using the velocity and position update formulas. In the second while loop, we do something similar. W is equal to negative ball.m times G times J hat. F of d is the drag force, and the net force is equal to W plus Fd. Again, ball.velocity and ball.position are calculated using the velocity and position update formulas like we did in the previous slide. Here is a screenshot of output from running the program. For our results, we have the observed versus predicted position of the slinky graph. The orange line is the observed model and the blue line is the predicted model. Some similarities include similar trajectories and that the dip remained consistent across both lines. A difference is that the observed line, which is in orange, starts slightly higher than the blue line. Some possible sources of error include tracking errors. For example, misidentifying the exact point on the falling slinky. Another source could be timing issues. This could be caused by video lag on Tracker, which might cause delays. And lastly, we have code errors. This could be from code inaccuracies from the computational model as well as calculation errors. Concluding with the discussion questions, we have what does it mean? Does the bottom of the slinky stay stationary? The bottom of the slinky doesn't start moving when you release the top. It stays nearly stationary for a short amount of time because the tension in the stretched coils supports it against gravity until the collapsing motion from the top reaches it. The second discussion question is what if the slinky were twice as heavy? Would the bottom still stay stationary when you release the top? If the slinky were twice as heavy, the bottom would still initially stay nearly stationary because the effect comes from the tension in the stretched coils, not the weight. It'll start moving once the collapse from the top, essentially the top part of the slinky, reaches the bottom. Thank you for watching this video.